In the next few minutes, I'll show you what a cryptographic hash function actually is, the four properties it has to be useful, what SHA-256 produces, and why every byte of its output looks random, the avalanche effect that makes a one-bit change unrecognizable, what it means for a hash to be one-way and collision-resistant, where you meet hashing in real systems, passwords, file integrity, Git, blockchains, every signature ever, and the famous example of a hash function getting broken in public. Welcome to Defense Stack. We produce one concept a day, and each one stacks on the last, building the framework for security together. Let's dive into hashing. Last episode, we ended with asymmetric encryption solving the key distribution problem and leaving two things still unsolved. We can encrypt to a stranger, but we can't yet prove who sent what, and we can't detect tampering along the way. Both of those need a tool we haven't introduced yet, a different kind of primitive entirely. It doesn't encrypt anything. It doesn't have a key. It just takes data in and produces a fixed-size fingerprint out. That tool is the cryptographic hash function. Without it, signatures don't work, password storage doesn't work, file integrity doesn't work, version control doesn't work, and no blockchain has ever existed. It is the most used primitive in computer security. A cryptographic hash function takes data of any size and produces a fixed-size fingerprint. The most common one today is SHA-256. The 256 is the number of bits it produces, 64 hex characters of output, no matter what you put in. An empty string in, 64 hex characters out. The word hello in, a different 64 hex characters out. A 50 megabyte video file in, still 64 hex characters out. The output looks random, but it isn't random. The same input always produces the exact same output. That deterministic, fixed-size, random-looking output is the fingerprint. A useful cryptographic hash function has four properties, and you need all four. First, deterministic. Feed it the same input, and you always get the exact same output. Second, one-way. Given just the hash output, you cannot work backward to find any input that produced it. The function is easy to compute forward and computationally infeasible to reverse, just like the trapdoor functions in episode 2. Third, collision resistant. Finding any two different inputs that happen to produce the same hash should be infeasible, even with the entire Earth's compute. And fourth, the avalanche property. Flipping one single bit of the input should change about half the bits of the output. The output looks completely different even when the inputs are nearly identical. The avalanche property is what gives hashing its magic. If I hash the sentence, "The quick brown fox jumps over the lazy dog," I get one fingerprint. If I change a single letter, the last word from dog to doe, I get a completely different fingerprint. Not slightly different, completely different. The two outputs share, on average, no more bits than two random strings would. This is essential, because it means an attacker who has the hash of some sensitive data cannot guess at it bit by bit. They can't tell whether their guess is almost right. Either it matches the full hash exactly, or it tells them nothing. There are several hash functions in use, and not all of them are still safe. The current default is SHA-256, part of the SHA-2 family standardized in 2001. It's what backs TLS, Bitcoin, Git, and almost every signature you'll see in production. SHA-3 and Blake 3 are newer alternatives, different internal designs, both considered strong. The two you must never use are MD5 and SHA-1. MD5 was broken in 2004. Researchers can find collisions in seconds. SHA-1 was broken in 2017 when Google demonstrated a real collision. Both still appear in legacy systems and need to be replaced wherever they're found. The first place you meet hashing in production is password storage. A real system never ever stores your actual password. It stores the hash of your password. When you log in, the server hashes whatever you typed and compares the hash to the stored hash. Match means correct password. Even the database administrator can't read your real password. There is no path back from the hash. If the database is stolen, attackers walk away with hashes, not passwords. There's a complication. Naively hashing a password is too fast, so attackers can guess billions of common passwords per second. The fix is deliberately slow hash functions like bcrypt or argon2, which we'll cover in a later episode specifically about password storage. Hashing shows up everywhere a system needs to detect tampering, identify content, or verify integrity. When you download a Linux ISO, the project publishes its HA256 hash. You hash your download and compare. If they match, you got exactly what was published. No corruption, no tampering. Every commit you've ever made in Git has an ID that is literally the SHA1, soon SHA256, of the commit's contents and its parent's hash. The entire Git history is a chain of hashes. Bitcoin and every blockchain since use SHA256 for transaction IDs, block IDs, and the mining proof of work itself. Content address storage systems use the hash of a file as its lookup key. Same content, same hash, never duplicated. What happens when one of these gets broken? The most famous example is from 2017. Google's research team announced an attack called Shattered. They produced two completely different PDF files, different titles, different content, different appearance, that had the exact same SHA1 hash. It took the equivalent of about 6,500 years of CPU time on a single core, but with cloud compute it became practical. The moment a collision exists, every signature and every integrity check that relied on SHA1 is suspect. An attacker can substitute one document for another, and the fingerprint still matches. This is why moving away from broken hashes urgently matters, and why every protocol is designed so the hash function can be swapped out. There's one important variant of hashing worth knowing before we leave the topic: HMAC, or Hash-Based Message Authentication Code. Plain hashing tells you whether a message has been tampered with, but only if you can independently trust the hash itself. If an attacker can rewrite both the message and the fingerprint in transit, the integrity check is meaningless. HMAC fixes this with a small twist. Instead of just hashing the message, you hash the message together with a shared secret key. The output looks like a normal hash, but only someone who has the key can produce or verify it. HMAC is what authenticates every AWS API request, every signed JWT, and every webhook your server receives from services like Stripe or GitHub. The catch is, both sides need to share the key in advance. Tomorrow we generalize the same idea to public and private keys, which lifts that restriction. That's what a digital signature is. That's the end of this concept. But each video stacks on the last. Subscribe, and we add the next layer tomorrow. So that's hashing. Fixed size fingerprints, one-way by design, collision-resistant in practice, and the avalanche effect that makes them untraceable. SHA256 as the modern default, MD5 and SHA1 as the cautionary tales. Passwords, file integrity, Git, blockchains, and everything else that needs to detect change. The simplest primitive in cryptography, and arguably the most used. 3 episodes in, we now have the building blocks for the next big payoff. Tomorrow, digital signatures, where hashing and asymmetric encryption finally stack into something more than the sum of their parts. Thanks for watching.